Hi all, this is Dr. K.G. Shanti, Professor, ECE Department, R.M.K. College of Engineering and Technology. In this video, I am going to talk about transmission lines and waveguides, a subject which will act as a basis for the understanding of the subjects like antennas and wave propagation, microwave, RF, which you will study in your higher semesters. And especially today we are going to see the unit 1 of transmission lines and waveguides. The various topics will be discussed in this video are going to be general theory on transmission lines, types of transmission lines, characteristic impedance of symmetrical networks, a line of cascaded T sections. The objectives of transmission lines and waveguides. It introduces the various types of transmission lines and its characteristics. It provides a thorough understanding of high frequency line, its power and impedance measurements, to solve different types of transmission line problems using Smith chart, to understand the characteristics of TE, TM and TEM waves in parallel planes, and to give a different very depth insight of different types of waveguides and the distribution of electromagnetic fields within the waveguides using Maxwell's equations. Now the syllabus of the transmission lines and waveguides, it is broadly organized into 5 units. First unit is Introduction to Transmission Line Theory. Second unit talks about high frequency transmission lines. Third unit talks about impedance matching in high frequency lines. Fourth unit talks about guided waves between parallel planes. And fifth unit talks about waveguides. This slide very clearly explains the outcomes on completion of this course of transmission lines and waveguides. A student will be able to solve transmission line equations and its parameters, explain about signal propagation at radio frequencies, illustrate impedance matching by steps using Smith charts, investigates the various field components in parallel planes, examine the field components in rectangular and circular waveguides, and discuss the principle of cavity resonators. The textbooks that are used for transmission lines and waveguides are John D. Ryder, Networks, Lines and Fields by Prentice Hall, India. Then the other book is David K. Cheng, Field and Wave Electromagnetics, Pearson. And references are Edward Jordan and Ballman. Next is Electromagnetic Field Theory by J.S.N. Raju, Joseph Administer Electromagnetics, Umesh Sinha, Transmission Lines and Networks, and Fundamentals of Electromagnetics by Michelson. And the commonly given book for all our students is going to be Transmission Lines and RF Systems, which is authored by myself, Dr. K.G. Shanti. Now, the first unit, Unit 1, Introduction to Transmission Line Theory. Now, what does it talk about? It gives a brief outline about the various types of transmission lines, transmission line theory, general theory on transmission lines, which means that we will be studying about what are the various line parameters, a line of cascaded T sections, where we will derive about Z0 and gamma, transmission line general solution, the infinite line, wavelength, velocity of propagation, waveform distortion, the condition for a distortionless line. We will study about what is reflection coefficient, and we will be studying about reflection factor and reflection losses. Right. Now let us do how a transmission line will look like. Now see here, this is the generator circuit and this is the load circuit. Now if suppose I want to transmit a signal from the generator circuit to the load circuit, the medium of transfer that carries information from the source to the load is going to be called as a transmission line. So it can be viewed as a two-port network connecting a generator to the load at the receiving end. Right. Now, before proceeding on with the transmission line theory concept, we have to know what is called as lumped parameters and distributed approach. Now, whatever components what we see in our lab, say for example, a resistor can be asked as a 1 kilo ohm value, a capacitor can be, you can ask for a capacitor of 1 microfarad, you can ask for a inductor of 1 Henry. So whatever we ask, a lab technician will be able to give you all those in the lab. Those parameters or those values what you get in a lab, they are called as lumped parameters because their value is concentrated at a place. But we have what is called as a distributed approach. In the case of a transmission line, you cannot say that this is the value of resistance that is present at a point on a line. This is the inductance, this is the capacitance, which means that the approach that is used on a transmission line is called as a distributed approach. Now, what is meant by a transmission line? It refers to a device that is used to transport energy or signal or information from one location to another. You have various types of transmission lines. An open wire line, which the other name for it is going to be a parallel wire line. You have what is called as a cable. You have what is called as a coaxial line, waveguides, microstrips, optical fibers. Right? These are the various types of transmission lines. The pictures will be shown in the next slide. Now let us look into the various types of transmission lines. A two-wire line. Now this is what we see in our day-to-day life. Now if you see the transmission of electrical power, right? Now the electrical cables, whatever we have, is a two-wire line. That is a pair of wires separated by a small distance. And this is one good example, once again, which we see in our day-to-day life, coaxial cable. Now when you look at your TV, the cable connection that connects to your TV is a coaxial cable. Now what's a coaxial cable? You have an inner solid conductor and an outer conductor separated by means of a dielectric. In the case of an open wire line, you have two solid conductors separated by means of a distance. Now as we move on with the higher frequencies, the size of the devices comes less, and this is a parallel plate guide, this is a rectangular waveguide, and this is a microstrip line that is used for connecting antennas. Right? So these are the various types of transmission lines. Now a still better diagram of an open wire line where you have two conductors separated by means of a distance, and this A represents the diameter of each conductor. A coaxial cable, see here, this is the inner solid conductor, this is the outside conductor, you have outside conductor, then you have insulation in between the two conductors. A is the radius of the inner conductor, B is the radius of the outer conductor, and this is the dielectric that is present between them. Okay. Next is the waveguides, which we can go and see in our microwave lab. We have a rectangular waveguide, right? A circular waveguide. So all these are microwave components. Right. The next topic what we are going to see is going to be called as a symmetrical network. Now what is the necessity for studying a symmetrical network, right? Now any transmission line can be made up of a number of small sections where each section is going to be called as a symmetrical network. Right. Now what is meant by a symmetrical network? Now look at this network. If I look from here or if I look from here to this side, right, the properties are going to remain the same. See here, if I look from here or when I look from here, the properties of this network remains unaltered. Such a network is going to be called as a symmetrical network. So any transmission line can be thought of made up of a number of small symmetrical sections like this. You can have n number of sections connected in cascade to form a transmission line. Now in this particular slide we are going to study about the characteristic impedance of symmetrical network. Now see here. When you look into this T network, the example what is shown is here is a symmetrical T network. We are going to find out the input impedance, right? For a symmetrical network, if the load impedance is Z0, then input impedance is also Z0. So that is what is given here. So Zn is equal to Z0, right? And how do I calculate? Z1 by 2, this is in parallel with, these two are in series, in parallel with Z2. This entire thing is in parallel to, series with Z1 by 2. So that is what is written here. Z1 by 2 plus Z2 in parallel with Z1 by 2 plus Z0. Then I apply the parallel rule, product by sum. Then what I do? Take an LCM, split the terms, cancel the common terms. I get the expression for characteristic impedance of a T network. What is the characteristic impedance of a T network? Z0 is equal to square root of Z1 square by 4 plus Z1 Z2. The transmission line is considered to be made up of 4 parameters: a resistance R, an inductance L, a capacitance C, a conductance G. When I have a pair of wires carrying current, each wire will offer some amount of resistance to the current. The energy is being transmitted from one end to another in terms of inductance. That is, any current conducting carrier will have energy stored in magnetic field accounted by inductance. A pair of wires separated by a small distance will give rise to capacitance effect. And if I have a pair of wires separated by means of a dielectric, and if the dielectric is not perfect, then there will be a small amount of leakage current that is accounted by the conductance G. Right? Now any transmission line can be thought of made up of a number of symmetrical T sections connected in cascade like this. Any transmission line will have a number of T sections connected in cascade like this, and if the characteristic impedance is Z0, that is, if the line is terminated in Z0, then the input impedance will also be equal to Z0. Now I am going to show you the equivalent circuit of one section of a transmission line. See here, when I look into this one section of a transmission line, you have a series inductance L, you have a resistance R. This inductance and resistance are forming the series arm of your symmetrical network, right, which is accounted by Z del X, where del X is the length of the small incremental line. So what I have a resistance in series with an inductance, and across the shunt I have a capacitance and I have a conductance, right. Now this is series elements R and L accounts for Z, and G and C accounts for Y. A line of cascaded T sections. Right, now as I told you earlier, a transmission line can be thought of made up of a number of symmetrical T sections connected in cascade like this. Right, and if it is terminated in Z0, then the input impedance is also going to be equal to Z0. And we have already derived the equation for the characteristic impedance of a T section. It is ZOT is equal to square root of Z1 Z2 plus into 1 plus Z1 by 4 Z2, where Z1 is the series arm and Z2 is the shunt arm. Right. Now the relationship between the sending current and receiving current. IS by IR is equal to e power n gamma, where n accounts for number of T sections. Gamma is the propagation constant. Right? What is gamma? Gamma is equal to alpha plus j beta. What is alpha accounting for? The attenuation. What is beta accounting for? The phase shift. Right. And this equation e power gamma, where e power gamma is equal to e power alpha plus j beta, can be written in terms of series and shunt arm impedances as 1 plus z1 by 2 z2 plus square root of z1 by z2 into 1 plus z1 by 4 z2. Right. Now this is an incremental section where you have L, R, G and C. Right. Now look into the series impedance. Z is the series impedance, which is R plus J omega L, and the unit of impedance is ohms per unit length. And Y is the shunt admittance. It is G plus J omega C. It is mhos per unit length. Right. Now what we are going to do is we are going to derive the characteristic impedance of a section of a transmission line. For this, I start with the characteristic impedance of a T section. Right. What we had, Z0 is equal to square root of Z1 Z2 plus Z1 square by 4. Now what I do, I take Z1 Z2 common. When I take Z1 Z2 common, I have 1 plus Z1 by 4 Z2. Right. Now what is Z1? What is your series arm? Z into del X. What is your shunt arm? Right. This is impedance. In terms of admittance, what will I have? 1 by Y into del X. Right. Now replace Z1 and Z2 by Z1 is equal to Z del X and Z2 by 1 by Y del X. So when I substitute it, what will I have? This del X get cancelled. Right. So what will be my Z0 is nothing but square root of Z by Y into 1 plus Zy into del X the whole square by 4. If del X approaches 0, what will happen to the second term? The second term will vanish. So what will I have? Z0 is equal to square root of Z by Y. Or what is Z0? It is nothing but, what is Z? R plus J omega L. Y is G plus J omega C. So what I get? Z0 is equal to square root of R plus J omega L by G plus J omega C. So this is the equation for characteristic impedance of a transmission line. Right. Now let us look into this part of the equation. Square root of Z1 by Z2 into 1 plus Z1 by 4 Z2. Now look at this term 1 plus Z1 by 4 Z2. Right. Now that can be written as 1 plus Z1 by 4 Z2. When I take it out of the square root, I'll have it as 1 by 2. Right. That I'm going to expand by using 1 plus x the whole power n formula. What is it? 1 plus nx plus n into n minus 1 by 2 into x square. Right. So what I have, this square root of Z1 by Z2 is remaining the same. 1 plus, what is n? 1 by 2. X is Z1 by 4 Z2. Right. N into n minus 1 is minus 1 by 8. Z1 by 4 Z2 the whole square. So this term 1 plus Z1 by 4 Z2 the whole power 1 by 2 has been expanded by using the binomial theorem. Right. Now you have this term of e power gamma. E power gamma, I have 1 plus Z1 by 2 Z2 plus the term under the square root has been replaced by what we derived in the previous slide. So this we have. Now what I am going to do is I am going to rearrange the equations and terms. So 1 plus Z1 by 2 Z2 plus square root of Z1 by Z2, that is I am expanding, right? And then I have 1 by 2 here, 1 4 here, 4 2s are 8. So 1 by 8 Z1 by Z2, this one into square root of Z1 by Z2. In the same way, 4 square is 16, 16 multiplied by 8 is 128, and I have the third term. Now what I am going to do is I am going to rearrange it. This third term is coming to the second place and second term is moving to the third place. So how I rewrite? E power gamma is equal to 1 plus square root of Z1 by Z2 plus this 1 by 2 into Z1 by Z2 can be written as what? Square root of Z1 by Z2 the whole square plus the third one. What is the third one? Z1 by Z2 can be written as square root of Z1 by Z2 the whole square. Already 1 is there, so Q, and so on. Right? Now this is one set of equation we have. Here I am applying Z1 is equal to Z into del X and Z2 is equal to 1 by Y del X. Right? Now I am applying that into this formula. E per gamma into del X plus square root of Z1 by Z2. When I apply Z1 is equal to Z del X, z2 is equal to 1 by y del x, I get square root of zy into del x. So I replace z1 and z2 by this way and I get this expression. Now to the same LHS, I apply series expansion formula. So e per gamma into del x is nothing but 1 plus gamma into del x plus gamma square into del x square by 2 factorial plus gamma cube into del x cube by 3 factorial by using this formula. Now what I am going to do is equate the two values of e per gamma into del x, right? So I have a e per gamma into del x. I write down both the formulas, one on LHS and the other on RHS, and I have cancelled that one in both sides. So I have this. Now what is the next step I am doing? Dividing throughout by del x, right? So when I divide throughout by del x, I get gamma plus gamma square del x by 2 plus gamma x cube del x square by 6 plus so on is equal to square root of zy plus square root of zy the whole square into del x by 2 plus square root of zy the whole cube into del x square by 8. Right? Once again, if I use the approximation, del x approaches 0, I get gamma is equal to square root of zy, where z is equal to r plus j omega l and y is equal to g plus j omega c. And this gamma is the propagation constant. So two important equations we have derived. One is z0 is equal to square root of z by y and gamma is equal to square root of z into y.